Hi everyone. Today we are talking about kites and trapezoids, which are two more types of quadrilaterals. These quadrilaterals are different from the last set of quadrilaterals we talked about. First of all, remember quadrilateral is any figure that has four sides. Okay? So any shape that has four sides we can call a quadrilateral. And the first major quadrilateral we talked about was the parallelogram. And then after we talked about all of the properties that a parallelogram has, we talked about two main types of parallelograms. There's the rhombus, which has four congruent sides and is a type of parallelogram. And there's the rectangle. Okay. And if you cross a rhombus and a rectangle, you get a square. So a square is also a type of parallelogram. So today we're talking about two other quadrilaterals that are not parallelograms. Okay, remember parallelograms have two sets of parallel sides. So the ones we're talking about today do not have parallel sides. And what we're talking about today are kites and trapezoids. Okay? So you may want to take a look at the quadrilateral hierarchy in the back of the room. Just to get an idea of where these figures fall on the overall hierarchy or family tree. The hierarchy is just a fancy way of saying like a diagram that shows the relationship. So the quadrilateral hierarchy is like this figure here. This is considered to be a hierarchy of these four items. So let's start with a kite. A kite is a quadrilateral with two pairs of consecutive congruent sides. I'll give you a minute to write that down and then we'll break down that definition. So remember, quadrilateral just means a figure with four sides. And then consecutive. Consecutive, remember, means next to each other. Okay? So a kite is a four-sided figure where both of the consecutive pairs of sides, or both of the pairs of sides that are next to each other, are congruent. So if you look down here in this figure, these two sides are next to each other and they're equal, and these two sides are next to each other and they're equal. This is not a parallelogram because in a parallelogram the opposite sides have to be congruent. In this figure the consecutive sides are congruent, so that's different from the opposite sides. So let's talk about some things we know about kites. Okay? In a kite, the diagonals are perpendicular. And remember this, we talked about this with rhombuses just yesterday. In a rhombus, the diagonals are also perpendicular. Do you remember what perpendicular means? Hopefully, you're all jumping out of your seat hoping to say the right answer is that it makes a right angle. So in a kite, when you draw those diagonals in, you get a right angle. And then you also know that this pair of angles is congruent, okay? It's not both sets of angles because this angle and this angle are not necessarily congruent. But these two, the ones that are between the sides that are not congruent, so like this side and this side are not congruent, so I'm looking at that angle in between. And this side are not congruent, so I'm looking at that angle in between. Some vocabulary for you that might be a little bit helpful is in a kite, the points that are between the congruent sides, so like this side and this side are congruent, so I'm looking at the point in between them, and this side are congruent, and I'm looking at the point in between them. Those are called the ends of the kite. So if you ever hear me say the ends of the kite, A and C, that means that A and C are the 2 points between the congruent sides. And so in this theorem, what I'm talking about are the angles that are not at the ends. Okay, questions on that at all? Okay. Okay. Example 2. In kite ABCD, measure of angle DAB is 54 and CDF is 52. Find angle BCD. So this, remember I told you with one of these problems, the most important thing to do is to write your measurements on your diagram right away. So angle DAB, again I'm going to trace that, DAB, so you can see the corner is angle A. That means this whole thing is 54. And angle CDF, so CDF is 52. This is 52. And I want to find angle BCD. So I want to find this angle up here. Let's see. How would I go about this? Well, here's what I would probably do. Okay. For now, I actually wouldn't focus on this 54 at all. I suppose there are some ways that you could use it, but I can do this without the 54. I would look at this right here as a right triangle, because again, we just learned that these diagonals have to be perpendicular. So if I know this is 52 and this is 90, I can do 180 minus 90 minus 52. And that should be 38 degrees. What that gives me is this angle up here. Okay, that gives me that my angle in blue is 38 degrees. Okay, so again, looking at this as a right triangle, this and this and this have to add up to 180. So if I've got these two, subtract those from 180 and I get 38 up there. Now that question asked me for angle BCD, so it asked me for this whole thing. And we didn't cover it as a formal theorem, but you can probably see this diagonal kind of splits the shape in half. It's a line of symmetry, so this top part is exactly equal to this bottom part, which means that this angle and this angle are exactly congruent. So if that's 38, then this is 38, and the whole thing put together, angle BCD would be 38 times 2, or 38 plus 38, which is 76 degrees. Okay. Again, probably some other ways you could have gone about that, but that's the way that came to mind for me. Let's try another one. I think our numbers are the same here. DAB 54. So again, this is 54. And CDF is 52. Let's see what it's asking me for. Angle ABC. Okay, ABC is this angle here. Okay, and I'm actually going to refer back to what we found on the last slide. Actually, it probably would have been easier if I put these all in one slide for you, but that's okay, you'll make do. We just found a second ago that this angle was 38. Okay, and if this whole angle is 54, think about how you could get each one of these smaller angles. Think for a minute. Do you know? If this whole thing is 54, how could you get each of these smaller ones? Take the 54 and divide it by 2. Okay, 54 divided by 2 is 27. So that means that this angle, this smaller angle, is 27. Now why did I go to all that trouble? Because really what I'm trying to find is ABC. I'm trying to find this. Can you see now that I have a different triangle? I have this triangle up here. And I've got 27 degrees here and 38 degrees here. And and I'm looking for this angle. So again, I can do 180 minus 27 and minus 38. And let's see, that's going to give me, that leaves me with 115 degrees. So again, here's my triangle that I'm focusing on. I've got 38 and 27, and this is my mystery angle. So take those two, subtract from 180, and you end up with 115 for the measure of ABC. One more with those same numbers. We write those in again. We've got 54 here, 52 here. And we just found some other ones, but we'll see what we need. Angle FDA. So angle FDA is down here. Okay, it's this. Again, try to look for a triangle somewhere that you can work with. And what I would probably do here is I would look at this triangle. Now it looks like you don't know much about that triangle, but you should know this. What is that angle going to be? That's a right angle. And then up here, we took that 54 a second ago and divided it by 2 to find that each one of those smaller angles is 27. So now, it's not letting me erase what I want to. That's okay. I know this smaller angle is 27. So if I look at this as one right triangle, I have a 90, I have a 27, and then I have my mystery angle. So let's take 180 minus 90 minus 27, and we should end up with 63 degrees. Okay, so 63 degrees is the measure of angle FDA. Okay. Okay, enough about kites. On to trapezoids. A trapezoid is a quadrilateral with exactly one pair of parallel sides. Okay, so a parallelogram had two pairs. Trapezoid has one pair. And we have different names for the sets of sides. So in a trapezoid, you're going to have one pair of sides that's parallel, one pair that's not. The bases are the sides that are parallel, and the legs are the sides that are not parallel. Let me give you a picture to go with that. And then I'll give you a minute to copy down those words if you need to. I want to point out some other terminology here for you. Okay, so you've got the bases. The bases are the two sides that are parallel. Remember that symbol right there means parallel. So the bases are these two. The legs are your two that are not parallel. And then the base angles. Okay, the base angles are the angles that are on the bases. So this is considered one pair of base angles because they share the same base. Here's your base angles for that base. Then this base also has base angles. That's going to be important when we talk about what's called an isosceles trapezoid. Okay, some things to know about trapezoids. First of all, I mentioned it just a second ago, but there's a certain type of trapezoid called an isosceles trapezoid. An isosceles trapezoid is a trapezoid with congruent legs. Now I want you to think about where you've heard that word isosceles before. Isosceles, triangles, remember, had two congruent sides like that. An isosceles trapezoid has four sides, so it's not a triangle. And these sides are parallel, that's what makes it a trapezoid. But then you've got these two sides congruent. So hopefully you can sort of see the similarities between an isosceles triangle and an isosceles trapezoid. Okay? There's a lot of things we know about isosceles trapezoids. Okay? One of them is that in an isosceles trapezoid, and this is what I meant a minute ago when we talked about base angles, in an isosceles trapezoid, the base angles are congruent. Okay, so if this is a base, then the two angles on that base are congruent. And if this is a base, then the two angles on that base are congruent. Okay? Think of it like if there were a line of symmetry right down the middle here, these angles would match up and these angles would match up. Okay? And then this next theorem is sort of a converse of this previous theorem. This theorem, 6-6-3, which you don't have to know the numbers, I just want you to know which one to look at, is saying that if you know it's an isosceles trapezoid, then you know the base angles are congruent. This next one says if you know the angles are congruent, then you know it's an isosceles trapezoid. Okay, so these kind of go hand in hand. Just one's the converse of the other. You could put the two of them together and write it as a biconditional. And then this next one is an interesting one. A trapezoid is isosceles if and only if its diagonals are congruent. So remember, diagonals are those lines that you draw across the paper, or I'm sorry, across the shape, across the quadrilateral. In an isosceles trapezoid, the diagonals are congruent. So the distance from B to D is the same as the distance from A to C. Can you think about where else you've seen a figure with congruent diagonals? A rectangle. A rectangle has congruent diagonals. Okay, so those two red lines, those are congruent in a rectangle. However, in a rectangle, the pieces of the diagonals are also congruent. All of these smaller pieces are also congruent to each other. So the distance from here to the middle is the same as the distance from here to the middle. Okay, in an isosceles trapezoid, the two red lines are congruent, but you can see that this distance is not the same as this distance. Okay, so that's that's the difference between a rectangle and an isosceles trapezoid. Okay, so we've got an isosceles trapezoid here. It wants us to find angle A. Okay, now be careful. Don't assume that it's going to be 100 just because 100 is the only number on your paper. Remember, this is not a parallelogram. Okay, parallelograms have opposite angles congruent, but this is not a parallelogram. Trapezoids, especially isosceles trapezoids, have base angles congruent. So I would know that this angle over here was 100. C and D are going to match. But how could I get those other two? Well, here's what I want you to think of. I want you to go back a ways to when we had two parallel lines, because we know those two are parallel, and a transversal. Okay, so focus on just the blue lines. And then I want you to think about this angle and this angle, and what you might know about those two angles. They're on the same side of the transversal. They're both up here. Okay? And they're in between the parallel lines. That makes them same side interior angles, and that means that they are supplementary. And if they're supplementary, that means they add to 180. Okay? If they're supplementary, they add to 180. So, if I look at this angle and this angle, these two added together have to make 180. If this is 100, what does this have to be if they have to add to 180? Well, you're probably able to just reason that out, but in case you need to see it mathematically, the total is 180. I can subtract 100, and that leaves me with 80. So that means this angle A is 80, and also angle B is 80. Okay, because those are base angles. Those are on the same base. Here's your base, and those two are your base angles. Now, something else I want to point out, that maybe stumped you a little bit. Be careful when you're trying to figure out which sides are the bases. Remember, the definition of base is the two sides, the two sides that are parallel, okay? Sometimes they're going to be on the bottom. I know you always think base is on the bottom, but it's not. Sometimes they will be, but sometimes they'll be like this, where they're up and down, okay? So just remember that your bases are the sides that are parallel, no matter how your trapezoid is laid out. Okay, KB is 21.9 and MF is 32.7. And of course, the first thing we are going to do is put these numbers on our picture. So KB 21.9. And FM is 32.7. And I want to find, I'm betting I'm finding JB. Oh, sorry, FB. Oh, I am finding this piece. Okay. Well, we know the whole thing's 32.7. So we're going to end up doing 32.7 and subtracting off whatever this piece is, because this is the piece we want to cut off to get what's left over. So again, if we're looking for this, we want to cut this piece off of the whole thing, which is 32.7. So that one that I marked with the squiggle, how long is that? Hopefully you're seeing that it's 21.9. Okay, I know I said earlier that the diagonals are not cut into congruent pieces. They are not. But the two smaller pieces are going to match up and the two larger pieces are going to match up. And we could do a proof of that, but I'm not going to make you do that. So just so you know, in an isosceles trapezoid, they don't cut so that all four pieces are equal. Okay, like for example, this piece and this piece are not congruent, but the two small ones and the two big ones are congruent. That's an important thing to know for a problem like this one. So I would do 32.7 minus 21.9, and I would end up with, I believe, 10.8. I'm doing that in my head, so I hope that I did that right. Let's see. Yes, that should be right. Okay, so this length from F to B would be 10.8, because 10.8 plus 21.9, because it's equal to this one, would give me 32.7 total. Okay, next up, find the measure of angle F, which is up here. Again, don't mix it up with a parallelogram. You're not going to say that this and this are equal. We're going to have to do something kind of like we did before. If this is 49, then we know the other one on the same base is 49. And I knew it was those two because this is my base, so that's the line they share. Okay, so then what do we know about the consecutive angles, the angles that are next to each other? Well, if these two lines are parallel, and this is my transversal, there's a parallel line, there's a parallel line, there's my transversal. Imagine that was straighter. If that's two parallel lines in a transversal, these two are going to have to add up to 180. So again, I would do 180 minus 49. And you should end up with 131 for angle F. So then what would angle G be? Angle G would match angle F, which is also 131. What do you think you're going to get if you add all four together? Let's try that. 131 plus 131 plus 49 plus 49. Has to equal, type away. Should be 360. Remember how we talked about every triangle has 180 degrees? Every quadrilateral, so anything with four sides, doesn't matter what it is always going to have 360 degrees. So that might be helpful to you. Okay, last example. AD is 12x minus 11. Before I even know what this question's all about, I'm going to put that on my picture. Oh, I forgot what it was. 12x minus 11. So this segment here is 12x minus 11. And BC So this one is 9x minus 2. And it says, find the value of x that would make this an isosceles trapezoid. Well, it's going to be an isosceles trapezoid if these two diagonals are what? What do you know about the diagonals in an isosceles trapezoid? We just learned it. Same as a rectangle. The diagonals are congruent. And if they're congruent, that means that this has to equal this. So let's write an equation that says that. I would write 9x minus 2 equals 12x minus 11. And let's solve it. I always start, and I know you guys always, I always kind of go around the room and have you guys start off the equations. And however you started is fine as long as you're doing something that's mathematically correct. But the way I always start is I look at my x values first if I have an x on both sides, which I do here. I have an x here and an x here. And I move my smaller x value. So I see a 9x over here on the left, so I'm going to move the 9x. I'm going to subtract it. And that leaves me working with positive numbers for x, which is just makes it a little less likely that you're going to make mistakes. 12 minus 9 is 3x minus 11. And now that I've got the x's on the right, I want to move the numbers back to the left. So I'm going to add 11 because that was a minus 11. Okay, negative 2 plus 11 is 9. 9 equals 3x. From here, I would divide by 3. Divide by 3. And I end up with x equal to 3. That's the value that would make that an isosceles trapezoid. Okay, homework assignment tonight is lesson 6.6. I believe it's practice A that I left for you. Make sure that you're showing your work on any problems like this one. And I would be referring back especially to those slides in your notes where I list the theorems for you, because that's really where your properties are going to come from. That's really where your information about the shape is going to come from. Okay. Tomorrow we'll work to try to summarize some of these properties about quadrilaterals, and we'll review for our test. So good luck.